Hello and welcome to this course on low power VLSI circuits and system. This is the first lecture of this course. Topic is introduction and course outline, and here is the agenda of this lecture. First I shall discuss why low power is so important in the present day context. Then I shall discuss two terms, power and energy, and what are the differences, which one is important, in which context a particular parameter is important. Then I shall discuss various sources of power dissipation. So, whenever you are fighting an enemy, you should know their their limitations, their weaknesses, so that you can fight them. So, these sources of power dissipation will identify their limitations and dependence of power dissipation on various parameters. So, once we identify those parameters, it will be very useful to reduce power dissipation by controlling those parameters. Then I shall discuss about leakage power, and particularly why leakage power is becoming more and more important in the present day context. Earlier leakage power was not very important, but in the present day context it is becoming very important, and why it is important, that I shall discuss. And after that I shall discuss about impact of process parameter variation. What is happening as the device dimension is getting reduced, as we are going to deep submicron technology, the variations are becoming very important, and as a consequence various parameters like channel length, threshold voltage, these are no longer constant. So, they vary over a range, and there is a you have to take into account that variation. So, what is the impact of process parameter variation, that we shall briefly discuss. Then I shall mention about low power design approaches. What are the different approaches that has to be done for reducing power dissipation, and finally I shall give a course outline. Okay. So, let me now focus on why low power. First important requirement is the changing trend. As you can see, until recently performance has been synonymous with circuit speed or processing power expressed in terms of MIPS or megaflops. So, whenever a particular processor spec, people were telling what is the specification, people will say it runs on so many megaflops, that means so many millions of floating points operations it can do, or MIPS, millions of instructions it can execute. But now the situation is changing. You have to earlier power consumption were of secondary concern, that means people were more concerned about improving the power performance rather than looking at the power consumption. So, power consumption were of secondary concern. However, in nanometer technology, which we also call deep submicron technology, power has become most important issue because of several factors. Number one is increasing transistor count. As you know, as the device dimension is getting reduced, you are able to put more and more transistors on a chip, and as a consequence power dissipation is increasing and power density is increasing, and you have to give more attention to power. Then higher speed of operations. As you know, in the early years of microprocessors, the microprocessors used to operate in the megahertz range, few megahertz, 5 megahertz, 2 megahertz and so on. But now all the processors are operating in the gigahertz range. So, speed of operation has increased, and you will see later on the power dissipation is directly related to speed of operation, rather power dissipation is proportional to the frequency of operation of the processor. So, as the frequency of operation is increasing, you are getting higher speed of operation, the power dissipation is increasing, and you have to give more attention to power. And then greater device leakage current. In the early years, maybe up to 100 nanometer, leakage power was of no concern. Leakage power or the static power dissipation was very small, but that is no longer true in say 33 nanometer or 66 nanometer. And as a consequence, you have to give more attention to leakage power, and you have to develop techniques by which the leakage power can be reduced. And another important factor which is also becoming predominant, that is increased process parameter variability due to aggressive scaling. As you know, there is aggressive scaling is taking place from early years of 500 nanometer. We have come down to 45 nanometer, 65 nanometer, very soon 33 nanometer devices will be used to fabricate microprocessors. And when you do that, it is creating problems in yield because of process parameter variation. Various parameters, as I told, those channel length, threshold voltage, and those important parameters which affect the performance of a device is no longer constant. So, those variations are affecting the yield, and obviously yield is getting reduced as you are doing aggressive scaling. And not only yield, reliability is getting reduced because chip is becoming more vulnerable to failure, and it is becoming also very difficult to do the testing. So, yield, reliability and testing, these three are creating problems as we are going to deep submicron technology. So, what is the way out? Only way out is to go for low power. You have to develop chips which consumes lesser and lesser power. So, that is one of the most important reason for considering low power in the present day VLSI design context. Then packaging and cooling cost. As you know, the packaging and cooling cost is dependent on the power dissipation of the chip. So, you have to take out the heat from the core of the chip, otherwise it will start malfunctioning. And this packaging and cooling cost is increasing, and as you can see, contemporary high performance processors are consuming more and more power. So, you can see here that 386 processor used to consume only say 1 or 2 to 3 watts of power. Now, as you are going for more high performance processor like Pentium, you can see it has reached about 100 watts. So, whenever a processor is dissipating 100 watts, you have to develop suitable packaging and cooling technique. You may be, I do not know whether you have opened any PC, you will find that inside the PC, on top of the processor there is a big heat sink, and not only that, there is a fan. So, packaging and cooling is becoming very important, and unless you are able to reduce power dissipation, the packaging and cooling cost will keep on increasing. So, cost associated with packaging and cooling such devices is prohibitive. So, it is important to develop low power methodology to reduce the cost of packaging and cooling. Obviously, as you know, Moore's law tells that the cost also will fall. So, cost will fall only when the cost of packaging and cooling reduces. So, a low power methodology is very important to achieve this goal. Then comes the increasing power density. As I was telling, as you are putting more and more transistors on a single chip, as the device dimensions are becoming smaller and smaller, the power density is increasing, that is watt per centimeter square. So, that is increasing, and as you can see, starting from 8080 to various chips, the chip is becoming so hot, it is the power density is very close to hot plate. Hot plate is used for cooking. So, you know, there is a joke, maybe there was a joke that there is a cyber cafe where you know, you can not only check your emails, but you can order for omelette, and omelette will be fried by putting the you know, that container on the chip. It will be so hot. Yes, anyway, so we cannot allow this. So, you have to reduce the power density by applying suitable low power technique. so that it does not really go beyond this. Finally, the number of portable systems is increasing at a very high rate, and there is an increased customer demand for handheld battery operated devices, as you know, like cell phone, PDA, pump top, laptop, etc. And not only that, not only there is a high proliferation of portable handheld devices, their functionality is increasing. Earlier, as you know, cell phones were commonly used for talking, but now what is not in cell phone? So, everything is you are demanding everything from a cell phone. So, cell phones with limitless functionality and limitless power supply is the requirement, because whenever you provide limitless functionality, your power consumption will increase as you put more and more functions in a cell phone, like camera, then internet access, then voice recording, FM, radio, and so on. Its power consumption will keep on increasing. Unfortunately, as I told, but for maybe fortunately, growth rate of this portable equipment is very high compared to desktops or servers. The number of such portable devices like cell phones, PDAs, laptop, palm tops is increasing at a very high rate, and growth of this growth rate is very high. But unfortunately, all these devices are battery operated, and battery life is becoming is of primary concern, and unfortunately, the battery technology has not kept up with the energy requirement of the portable equipment. You will see that the power consumption is increasing at this rate. This is the power consumption of the devices or systems, and maybe battery technology is increasing improving at this rate. So, over the years. So, this is the battery technology, and as you can see, over the years the gap is increasing. So, the power consumption versus the battery technology, that means the capability of battery, power density of battery is definitely improving over the years, but power consumption is increasing at a much faster rate, and this gap is increasing. So, commercial success of these products is dependent on size, weight, cost, and computing power and battery life. So, whenever you go for selecting a cell phone, what you will look for? How long the battery will sustain, or whenever you go for purchasing a laptop, you will see that without charging it will, you can operate it for maybe 12 hours or maybe whole day. Commercial success of these products heavily depends on size, weight, cost, computing power and battery life. Obviously, size is dependent primarily on the battery size. You will see that in most of the portable equipment, battery size is dictating the size of the device, because that is the most important component, and its size is maximum. So, low power design methodology is very important to make them commercially viable. Finally, reliability. As I was telling, reliability is very important in VLSI chips, and as you can see, as the power consumption is increasing, temperature will keep on increasing unless you provide proper heat sink to dissipate the power. And you can see there are various failure mechanisms like thermal runaway, gate dielectric, junction diffusion, electromigration diffusion, electrical parameter shift, package related failure, silicon interconnect fatigue. These problems will keep on arising as the temperature increases, and it has been found that every 10 degree centigrade rise in temperature roughly doubles the failure rate. So, what is the conclusion? To make the chip reliable, it is very important to use low power design methodology, so that power consumption is small, rise in temperature is small, the chip can operate at a reliably. So, from the reliability point of view, low power design methodology is extremely important. Finally, impact on environment. US Environmental Protection Agency, it has been found that 80% of the power consumption by office equipment are due to computing equipment, that means computers and printers and other related devices, and a large part from unused equipment. This is irony. That means, if you visit some offices, you will find that computers and other systems are on, but they may not be used, but still they are on. So, those unused equipment also consume lot of power, and in fact, whenever this power is dissipated and mostly in the form of heat. And what you normally do? You have to use some cooling technique such as air conditioner to transfer the heat to the environment. So, that means, the heat that is being released by these computing equipment is ultimately released to the environment. So, it has impact on the environment, and to reduce adverse effect on environment, efforts such as those EPAs, Environmental Protection Agencies Energy Star program leading to power management standard for desktops and laptops has emerged. You know, nowadays situation is little different. So, whenever you are not using a desktop or a laptop, you will find automatically screen is becoming blank, and the power hungry components are automatically shut down by the power management circuit. So, that is actually a result of this this standard, power management standard for desktops and laptops. So, this concern about environment has led to drive towards green PC, and obviously, this consciousness about environment also dictating low power design methodology. You have to use low power design methodology, so that environment is not affected. So, I believe even now fully motivated about this requirement of low power methodology. You see, there are so many reasons for low power methodology. Okay. Now, let us now focus about about some of the technical things. Whenever we say power or low power, what do we really mean? There are three types of power dissipation. One is peak power. What is peak power? Peak power is essentially, so suppose you plot the power dissipation over time. So, this is your power dissipation. You will find that it is not really constant, depending on the application you are running. Sometime the power consumption is high, sometime it is low, sometime it is maybe very low, like that. So, the power dissipation varies over time, and you can see there are some points where it is drawing very heavy power, and this is your peak power. So, peak power is the maximum instantaneous power at a particular time, maybe T1 and here at time T2. So, peak power is the maximum instantaneous power. What it really affects? It affects the reliability of the operation of the system, because whenever this kind of heavy current is drawn, this current will flow through the power line. That means, the power supply has to deliver power through the power line to the chip or the VLSI circuit, and there will be, it has some finite resistance, and as a consequence there will be some voltage drop in that power line, and that will lead to what is known as glitch on the power line, and glitch on the power line may lead to malfunctioning of the chip and unreliable operation of the device. So, peak power essentially affects reliable operation. This is one type of power. Second is your average power. Average power what does it affect? So, this is the peak power, I mean how the power varies over time. If you take average, maybe it will be somewhat like this. This is the average power. This average power affects the packaging and cooling system. Packaging and cooling system. So, packaging and cooling is affected by the average power. That means, if the average power is high, you have to develop suitable packaging and cooling, so that the heat is taken out from the chip. Third one is energy. What do we really mean by energy? Energy, power is the rate at which energy is drawn from the system, maybe from battery or from the power supply. So, the rate at which energy is drawn from the power source is the power dissipation. So, in the context of battery operated systems, that means it affects battery life. Energy affects battery life. Let me explain with the help of this diagram. Here, as you can see, during the operation of a processor over time, you can see this is the average power dissipation P1. So, P1 is the average power dissipation. Accordingly, the packaging and cooling system has to be designed, and here the average power dissipation is P2. So, this line. So, this is expressed in terms of watt. Now, what is energy? Energy is the area of this, that means power dissipation, and this is the time. You have to multiply the time with the power dissipation to get the energy drawn from the power source, maybe battery. In portable systems, obviously this will be from the battery. That means, if this is let me draw this curve once again. Say this is the P1, and let us assume this is time T1. So, energy E1 is equal to P1 into T1. Now, let us assume here it is so this is your T2. T2 is double that of T1, and power dissipation is also half. So, here you can see E1, this E1 is equal to P1 into T1, and here E2 is equal to P2 into T2. So, average power dissipation is half, but the duration is longer. So, here you can see E1 and E2, these two are same, but the power dissipation is different. So, what can happen, sometimes you can reduce the power dissipation by slowing down the clock frequency, but again that will increase the computation time. So, energy drawn from the power source may remain same, but in the context of battery operated system, this energy is most important parameter, and usually it is expressed in terms of power into delay, power delay product. So, sometimes power and energy, these two terms are used interchangeably, although these two are different, particularly in the low power context, low power design methodology context. When you are considering the battery operated systems, there actually the energy is the most important thing. So, sometimes we will tell power, but actually you are trying to tell energy. So, when we say low power, essentially it is low energy. Okay. So, it is very essential to understand the difference between power and energy. Is it clear? Okay. Now, let us consider the technology that we shall be using. As you know, there are various technologies which have been used for the fabrication of IC. We are not considering the early systems like TTL, transistor logic, or PMOS or NMOS, which were used earlier. But in the present day context, CMOS is the technology of choice. CMOS is used for fabrication of all the VLSI chips nowadays, and this is the basic structure of a CMOS circuit. You have a pull up network of PMOS transistors, I shall discuss in detail later on, and here you have got pull down network of NMOS transistors, and here is the input which are going to the gates, and the output is taken from the junction of PMOS network and NMOS network, and this is the output. You note that there is a load capacitance given here CL. Now, you may be asking why CMOS is the technology of the choice? Because of its various advantages. What are the advantages? Number one is ease of fabrication. The fabrication technique has been standardized, matured, and now it is very reliable. That means, CMOS fabrication technology has matured and it has become very reliable over the years. Then it has got good noise margin. Later on I shall discuss in detail. CMOS provides you better noise margin compared to other types of circuits like NMOS or PMOS or TTL, and it is very robust. By robust means under different hazardous condition, like when there is change in supply voltage, when little bit of change in supply voltage, there is noise. Under that circumstances, it will operate reliably. CMOS circuits are more robust. Then lower switching activity. Later on we shall see the switching activity is lower in CMOS circuits, particularly in static CMOS circuits. Then good input output decoupling. This good input output decoupling arises because in CMOS circuits you will see that input is applied to the gate. So, you are applying input to the gate of a single transistor or a network of transistors, and you are taking output from the maybe from, let me draw once again. So, this is a PMOS transistor, this is a NMOS transistor. So, I have drawn a very simple inverter. So, you will be applying input to the gates and taking output from the, you can see from the junction of the source and drain. And since this input is of very high impedance because of silicon dioxide present here and here, there is a good input output decoupling in CMOS circuits. And later on we shall discuss about charge sharing problem, and you will see in CMOS circuit there is no charge sharing problem compared to other techniques like dynamic CMOS and other things. And as I mentioned, there is availability of matured logic synthesis tools and techniques which are available. CAD tools are available which can be used to synthesize CMOS circuits, and because of these advantages, CMOS is the technology of choice. Of course, in this world nothing is one sided. There are some disadvantages and difficulties which are listed here. You have got large number of transistors, because you are using, as you can see, 2 transistors. Although one transistor may serve the purpose to realize the same functionality, you are using 2 transistors. As a result, number of if you have got n inputs, here n is equal to 1, you have got 2 transistors. Similarly, if there are n inputs, you will require 2 n transistors. So, as a consequence, area is larger and delay is longer. So, because of this duplication of the transistors in the realization of CMOS circuits, the chip area is larger and delay is longer. And weak output driving capability. You will see whenever you are realizing a complex circuit, the output is taken through a chain of NMOS or PMOS network, and as a consequence resistance is high and driving capability is poor. Large number of standard cells required, substantial engineering effort for technology mapping. You will see whenever you realize a very complex circuit, you have to use different types of standard cells like inverter, 2 input NAND gate, 3 input NAND gate, 4 input NAND gate, 5 input NAND gate, 2 input NOR gate, 3 input NOR gate, 4 input NOR gate, and so on. So, then different types of flip flops and so on. So, you require a large number of standard cells and whenever you realize a circuit, and that step is known as technology mapping. You have to select different cells to realize circuit. So, that requirement is there, and later on we shall see there is glitching power dissipation in CMOS circuits because of the delay. As I mentioned, there is a delay, large delay in CMOS circuits, and that has led to glitching power dissipation, and also there is short circuit power dissipation, which I shall briefly discuss shortly. So, now comes the sources of power dissipation, and this is a typical CMOS circuit, 2 input NAND gate. I have shown 3 input NAND gate. I have shown, you can see it has got associated with a large number of parasitic capacitances. This is the load capacitance CL. Apart from that, there are other capacitances C1 at this junction, C2 at this junction. So, there are large number of parasitic capacitances which are present inside the circuit, and the sources of power dissipation in CMOS circuits can be broadly divided into 2 types: dynamic power and static power. So, dynamic power is essentially when the circuit is in active condition, when the circuit is in use, when you are changing the input, when there is a clock present in the circuit, that time whatever power dissipation takes place, we call it dynamic power dissipation. On the other hand, whenever the circuit is in standby mode, circuit is not in use, it has been kept in the standby mode. As I was telling, when the circuit is not used, that part of circuit is shut off. Shut off means you are not applying, not changing the inputs, you are not applying the clocks, and but unfortunately there will be some power dissipation even in that standby condition, primarily because of various leakage currents, and leakage currents can be broadly divided into 3 types: diode leakage current, subthreshold leakage current, and gate leakage current. Similarly, the dynamic power can be divided into 3 different types: switching power, short circuit power, and glitching power. Let me very briefly discuss about these sources of power dissipation. Switching power. Switching power is the most predominant component of power dissipation in CMOS circuits, and particularly this happens when the circuit is in dynamic mode. So, when the circuit is in dynamic mode, this power dissipation occurs. So, this switching power dissipation occurs due to charging and discharging of current. Charging of discharging of current leads to power dissipation. As I have told, it has got associated with some parasitic capacitances. When the output is becoming high, that means you have applied some input combination such that output is high. That time this load capacitor CL will charge from the source through this PMOS network, pull up network, and as it charges, some power will be dissipated in this pull up network because of its resistance. And similarly, when the output becomes 0, the charge which is accumulated in this capacitor when it was 1, I mean output was high or 1, that will get discharged through this pull down PMOS transistor, NMOS transistor network. Here there is NMOS transistor network. So, pull down NMOS transistor network, it will get discharged, and again power will be dissipated in this NMOS transistor network because of their finite resistances. So, the switching power dissipation is primarily due to charging and discharging of parasitic capacitances, and this power dissipation will be dependent on the supply voltage, load capacitance, and other activities, the switching activity, the rate at which the transitions occur, and so on. Later on we shall discuss about it in more details. Then comes the short circuit power. Short circuit power dissipation occurs because of slow change of the inputs. As you can see here, input is changing in a CMOS circuit. As the input changes slowly, like this. Say I have drawn it in a little exaggerated form. This is time and this is input voltage is changing, and let us assume this is your VDD and this is 0 volt and here it is time, and let us assume this is a inverter, simple circuit inverter. So, you have got a PMOS pull up network and NMOS pull down network, and here you have applied this V input, this is your V in. So, this is applied to this. So, initially as the input is increasing, you can see this voltage is less than the threshold voltage of this transistor, and at that time this transistor is off, this transistor is also off. But as the input voltage increases and as it reaches the threshold voltage of the NMOS transistor, then this transistor will turn on, and this transistor will turn on, and as you know, during that period this was already on. That means, during this period only PMOS transistor is on, but here from this, because input is 0 and so there is a this voltage gate voltage is get to source voltage is such that this transistor is on even for during this period, but this was off. So, there was no current flow, but from this point onwards both the transistors are on and it will continue till you reach VDD minus VTP. So, for this duration both the transistors are on, as a result current will flow through this path as if the VDD is shorted to ground, and this is known as short circuit power dissipation. So, short circuit power dissipation primarily arises because of slow change of inputs. So, power dissipation takes place even when there is no load or parasitic capacitor. That means, even when there is no capacitance here, this power dissipation will take place because the supply voltage is shorted to ground through this PMOS and NMOS transistor, and it may not be an inverter, it may be a complex circuit. In such a case, this will be a complex PMOS network and this may be a complex NMOS network, but there will be a current path through this circuit when the input is greater than VTN and less than VDD minus VTP, and this current, this power dissipation is known as short circuit current, short circuit power dissipation. Finally, the third source of dynamic power or dissipation is glitching power. This glitching power dissipation occurs due to delay, finite delay of the gates. For example, here you have got a two NOR gates, A and B is applied to this gate, output is Q1, and this Q1 and C is applied to the second NOR gate. Normally, whenever the input is 101, what should be the output at Q2? It should be 0. Similarly, when the input is 0 0 0, that means A is 0, B is 0, C is 0, output again will be 0. But you can see here when the input is 101, this output is 0, this output is 0, and it will change to 1. This 0 will continue for certain duration because of this delay. When this, but whenever it becomes 0 0 0, then this output will become 1, and this 0 will is responsible for this high output for a very small duration. That means, this input, whenever the input is changing from 101 to 000, because of the finite delay of these gates, there is a output the output is becoming high for a very small duration, and this is known as glitch. So, glitch is generated at the output because of finite delay, and as you know, there is a capacitance present here and there will be power dissipation in that capacitance. So, there will be glitching power dissipation on this output capacitance. So, this leads to glitching power dissipation because of finite delay of the gates. Okay. Then coming to the static power dissipation, that is your leakage power. You can see here a simple MOS transistor is shown. This is the source, this is the drain, and this is the gate structure, and different types of leakage currents are listed here, and this is taken from a paper by Kaushik Roy and his group. And here is the different leakage currents. I1 reverse bias PN junction diode current. So, this you have got here junctions, because this is a if this is a PMOS NMOS transistor, this will be N plus and this will be P type substrate. So, there is a junction here. Similarly, here there is a junction, this is N plus and this is P type substrate. So, in these junctions, the junctions are these diodes, it is forming some kind of diode, and those diodes will be reverse biased during normal mode of operation. As you know, when a diode is reverse biased, there is some leakage current, there is some reverse bias current. So, there will be reverse bias PN junction diode leakage current. Later on I shall discuss about it in more detail, and particularly although this current is small, but when the number of transistors is millions, then total leakage current can be substantial. Then band to band tunneling current, that too occurs in these junctions. The electrons will go from valency band to conduction band because of high energy acquired, high electric field present, and that leads to band tunneling current. Later on again I shall discuss about in more detail. Then third type of leakage current IC that flows through this channel is known as subthreshold leakage current. Normally we know that whenever the gate voltage is less than the threshold voltage Vt, this transistor is off, no current flows through the channel, but ideally this is not true. Even when the gate voltage is little more than 0, some channel current is flowing, and particularly if the input voltage is very close to Vtn, little less than that, then the leakage current is this subthreshold leakage current. This current is very high, and this is known as subthreshold leakage current, because input voltage is less than the threshold voltage. Even then there will be current flow through this channel. So, this subthreshold leakage current is substantial in transistors of smaller dimension, in particularly in deep submicron technology. Then gate oxide tunneling current, as you know, as the device size is shrinking, the size of the thickness of the gate oxide is becoming smaller and smaller. It is becoming so thin that it is a layer of few molecules, maybe 2 or 3 molecules of silicon dioxide. And what happens, the electrons, particularly electrons, they acquire so much energy that they cross that silicon dioxide layer, leading to what is known as gate oxide tunneling current. So, gate oxide tunneling current is flowing between gate and the substrate I4. Then gate current due to hot carrier injection. Hot carrier injection is due to that because of heavy electric field, the electrons acquire so much of energy, and they are termed as hot electron. So, and although hot holes are also possible, but they, because of their mass, heavy mass, they do not contribute much for this current. Particularly electrons are responsible for this hot carrier injection current. So, that also flow through this silicon dioxide. Then channel punch through occurs because as the dimensions are getting reduced, this particular source and drain is becoming very close, and their pinch of regions are becoming too close, and they may touch, leading to what is known as channel punch through, and as a result current will flow through the channel between source and drain. This is again a source of power dissipation. Finally, gate induced drain leakage voltage. So, particularly when the supply voltages are I mean large, drain voltage is large, and whenever gate voltage is large, that leads to what is known as GIDL current, gate induced drain leakage current, and this gate induced drain leakage current is becoming more and more predominant in deep submicron technology. So, these are the various sources of leakage power. I shall discuss about them in more details later on. Now, coming to leakage power, it is becoming more important because as you can see, the active power is increasing as we are going from one technology generation to next technology generation, as the device size is becoming smaller and smaller, but the leakage power, which is represented by standby power, is increasing at a much higher rate, and leakage current is increases at a faster rate than dynamic power in various technology generations. And as a consequence, you can see at some point the leakage power will be more than the active power, as it has happened here. For example, for 0.25 micron technology, the leakage power is very small compared to dynamic power. Dynamic power is more predominant, but as we are going from say 0.25 micron to 0.18 micron to 0.13 micron, as you can see, the leakage power component is increasing, and whenever it is 0.07 micron, that is your 70 nanometer, you can see the leakage power component is more than the dynamic power or active power. So, in the present day context, particularly we are discussing about deep submicron technology, circuits to be realized by using deep submicron technology, using 45 nanometer or 33 nanometer technology. There the leakage current leakage power dissipation will be more than the dynamic power, and so you have to give more attention to the reduction of leakage power. And another important factor is reduction of runtime leakage power is important. Earlier, you know, this leakage power was very small compared to dynamic power. That means, when the circuit was in standby mode, then power dissipation was considered to be very small. Only during runtime the dynamic power was considered to be important, but as leakage power is becoming more and more, during runtime you have to also consider the leakage power component in addition to the dynamic power. So, runtime leakage power is becoming important. Earlier the leakage power during standby was important. So, people used to reduce the leakage power only during standby mode. How to reduce leakage power during standby mode, but now you have to focus on the reduction of leakage power even when the circuit is in active mode or circuit is in runtime condition. Okay. Another important factor which is becoming important, that is your impact of process parameter variation. As I was telling here, how the process parameter variation affects leakage and performance is shown. You can see this is taken from a paper by S. Borkor and his colleagues, they are in Intel, and as you can see there is a 30% of delay variation. Here you can see the delay is varying 30%, 1 normalized frequency is here, it is 1 and here it is 1.3. So, there is a 30% variation of delay for the same IC. The I mean for different chips the delay has been measured. You can see for different chips the variation is this over this range, 30% delay variation, but leakage power variation is much more, 20x. That means 20 times leakage power variation is taking place for different devices manufactured by the same technology, and that too for 0.18 micron technology. And as you will go to smaller and smaller dimension, this component will be more and more predominant. So, low leakage chips with too low frequency must be discarded. As you know, you have to by how do you select yield? Yield is dependent on the how many chips that is being fabricated are usable. If it is slow, you have to discard it. If it is too leaky, consuming too much power, you have to discard it. So, low leakage chips with too low frequency must be discarded. high frequency chip with 2 high leakage must be discarded, and that is responsible for lower and lower yield. So, you have to develop techniques such that this process parameter variation is not much. The circuit is process parameter variation tolerant, and particularly this is becoming important because of this from one sided constant it has shifted to two sided constant. You can see in the early years of VLSI circuits, it was a one sided constant. That means, as you are reducing the channel length, you can see, I mean, devices were becoming smaller and smaller, the delay was increasing. I mean, as you are reducing the dimension, delay was reducing, power dissipation was also reducing. So, you are happily going for devices of smaller and smaller dimension, and that is the reason, that is, I mean, based on this Moore's law flourished. But what has happened nowadays, you can see, because of the increase in leakage power, you can see as the device dimensions are reduced, delay is getting reduced, but power dissipation is also increasing because of, primarily because of, that leakage power, increased leakage power, and as a result you have got a two sided constant. So, two sided constant means you have to discard these chips. Earlier you were discarding only these chips, but now you have to discard these chips as well as these chips. So, yield is becoming lower and lower. So, this is the situation of current and future technologies. Later on I shall discuss more about it in details, and you have to use some statistical technique. These parameters like channel length, threshold voltage, these are no longer you cannot assume them to have fixed values. They are now statistical parameter. They vary over a range with a peak at some point, and on both sides they reduce. So, you have to use some statistical technique to have higher yield. Now, coming to the degrees of freedom, we will see that these are, we have got these parameters in our hand: supply voltage, physical capacitance, switching activity, and threshold voltage. These are the parameters which you have to control, one or more, to reduce power dissipation, and based on that the basic approaches can be categorized as supply voltage scaling, minimizing switch capacitance, and minimizing leakage power. Our lecture will be organized around this. We shall discuss supply voltage scaling techniques, we shall discuss minimizing leakage switch capacitance, how we can do that, then minimizing leakage power primarily by controlling the threshold voltage. So, low power design methodology are to be applied throughout the design process. As you know, it is not a single step, you have got a number of steps that you have to follow in the design, starting from system level to layout level, and gradually refining or detailing the abstract specification or model of the design. So, these are the basic steps you normally follow: system specification to system level design, and then you get the behavioral description. From that you get you perform high level synthesis. High level synthesis provides you structural RTL description. You use that for logic synthesis, and from logic synthesis you get logic level net list. Use that for layout synthesis, and finally you get the layout for fabrication. So, throughout this design process you have to adopt low power design methodology, and you can see here the benefit is more and more at higher level of abstraction. I mean, if you can use low power design methodology at behavioral or algorithmic level, your gain can be 90 to 99%. That means, power dissipation can be reduced by 90 to 99%. In the architectural level, it can be from 10 to 90%. In the logic level, power dissipation can be reduced by 15%. In the circuit level, it can be reduced by 30%. In the layout level, it can be reduced within 20%. So, you can see, if you can use low power design methodology at higher and higher level, you will be more benefited. Okay. So, based on this discussion, we shall be I have developed a course outline. First I shall focus on background material, that means basics of MOS transistors, 4 or 5 lectures on basics of MOS transistors. So, I shall adopt bottom up approach, starting with transistor, then I shall consider inverter, then I shall consider more complex circuits, then systems, like that. So, basics of MOS transistors followed by MOS inverters, several lectures. These are various topics I shall cover in my lecture. Then MOS combinational circuits, both I mean combinational circuits and also MOS memory circuits I shall consider, and I shall see how you can use low power design methodology there. Then I shall switch to those lectures are essentially for developing background material. So that you can understand the low power design methodology and you can use them in a fruitful way. So, then comes the sources of power dissipation. I shall discuss in details various sources of power dissipation, both dynamic and static, as I told, short circuit power, switching power, glitching power, and then the various static power dissipation. And then I shall discuss about supply voltage scaling approaches at various levels of design hierarchy, how they can be used. Similarly, switched capacitance minimization approaches in different levels of design hierarchy for of system design. Then leakage power minimization approaches and various techniques used for leakage power minimization. Then some special topics also I shall consider, like adiabatic switching circuit, battery aware synthesis, variation tolerant design, then CAD tools for low power, which is also very important. So, this is the brief outline of my lectures, and with this we have come to the end of today's talk. In the next lecture I shall start with MOS transistors. Thank you very much.